This is negative orientation?
Yeah, so if we're going to use Green's theorem, we have to pay attention to that, all right? Right now, this is our C, isn't it? Our C is this path right here. Do you all feel like you want to do this Green's theorem? Do you feel like, or do you all want to do parametric representations of the three line segments? No, it's a closed region, right? This right here is D. So we should be able to use Green's theorem. But as has been pointed out, the orientation of our C right now is negative orientation. We're going clockwise, right? So Green's theorem applies if you have positive orientation. So how do you think things change? Just the sign, right? That's it. So if we want to do the line integral over C of this closed curve of f dot dr, to use Green's theorem, right, we need to change the orientation. So we need to imagine that thing backwards, right? Let me do it this way. How do I want to do this? Here's what I want to do. Just tell me if this makes sense to you. Is that okay?
You should make the whole thing negative?
Yeah, but why did I make it negative?
It's clockwise.
Yeah, because if I want to go this way, right, the theorem works if I were to have been going this way. So what I'm going to do is I'm going to go this way, I'm going to act like it's going the other way and then change the sign of the answer. So it's like if I want to change this direction, negative here, go backwards, then you have to change that to a negative. So it's like, yes, I want to go over C, which is backwards from what Green's theorem allows. Yes? Is that a question or comment? Concern? Observation.
So, the integrand in this
Yes.
integral,
Yes.
in positive orientation, it's derivative of q over x minus derivative of q over y. I guess that has something to do with the orientation, because if you think about it, if you distribute that negative through into the integrand, you get partial p over y minus partial q over x.
Yes.
You get those two flip.
Yep.
So I guess that has some connection to the orientation of the...
Yes. But that all goes back to the way you parametrize something. Because when you parametrize a line segment, right? Remember we said, like, if you want to go from here to here, you're going to do a parametrization, and then you're going to let t go from 0 to 1, right? But if you go the other direction, want to go from here to here, then your parametrization changes. You still go from 0 to 1 on t, but your vector equation for that line segment changes. So it's like everything gets flipped sign-wise because you're Am I making any sense? I don't know if I'm understanding your observation.
I just found it interesting. I guess that where that derivative of partial of q with respect to x minus partial of p over with respect to y.
Mm-hmm.
I guess that sort of comes from the orientation we're using, I guess. Or it has some... I guess I'm going to look at a proof of the Green's theorem.
Yeah, you got to look at I think you would have to look at the proof of the Green's theorem. What I'm trying to base this negative sign out here on, and why it's changed, is going back to when we were first talking about line integrals, which was in 13.1, I believe. Yeah, C versus negative C. That's where this is all really rooted from. Was it? Yeah, 13.2 then, right? Line integrals.
Orientation.
Right after example 3.
example. Yeah, there we go. So when you do a line integral, if you change the direction of the path, then the signs change, right? If you're doing it with respect to x or y, the signs will change if the path changes. And remember, the work integral, this work integral is p dx plus q dy. So you have both this one and this one. So if you change the path, they both change signs. So if they both change signs, then Green's theorem should also change signs. That's what I'm using for this. I don't think you need the proof. I think what the proof would help you see is why this.
Yeah.
Why this. Maybe next class, if we have time, which I know we don't, I could do a proof of the Green's theorem. And the book does do a proof. So you can read through that and see if it makes sense. All right, let's get back to this though. All right, everyone clear on what we're going to do? So if the path is negative orientation, then all we're going to do is take negative here. All right, so now this is double integral. Let's just keep that there over d. Partial of q with respect to x is just, ooh, it's not as nice as I thought it was going to be. What is it? 2x and then plus 2y cosine x, right? So that's partial of q with respect to x. And then I have minus now partial of p with respect to y. Oh, come on, are you kidding me? What's that? What's partial of p with respect to y? 2y cosine x dA, right? And these two cancel. So now we are at a double integral over d of 2x dA. Now this time we can't just pull something out and get area anymore because x is in there, right?
Do we not keep our negative?
Yeah, I don't know why I lost the negative. I'm sorry. That's my fault. Negative here, negative here. Thank you. I figured out why we lost it. I think I'm just getting old. I think that's what's happening. I've come to terms with it. That's why I need my students to stay sharp. All right, next, what? How are we going to do that? If this was a 1, we'd have area, but we don't. Right?
The
So-
area is made up of like partials with respect to your each components, right? Your x and y component. Like
What's it?
dA's, we're going to be like, dA is going to be like dx, dy.
Yeah, exactly. So we're just now back to a double integral. The beginning section of what was it, chapter 11? No. Double integrals 12.1, 12.2, 12.3. So we had double integrals over rectangles, double integrals over type 1 regions, type 2 regions, polar coordinates. So when we look at this, this is our double integral. This is our region. What type region is this? It's like a type 1 region, right? So if I look at this, what's my restriction on x? What's my restriction on y? So x is bounded between 0 and 2. My y's are bounded between 0 and... Yeah, you have to look at that as a function of x. So what is it, 3x? Y is equal to 3x. So now we're just gonna crank this thing out. We're gonna have negative integral 0 to 2, integral 0 to 3x, and we're integrating 2x dy dx. There we go. And whatever that is, that's the work done. Make sense? May as well get you an answer. This one's easy enough to type in, so we're going to go 0 to 2, 0 to 3x. We're integrating negative 2x with respect to y, then x. Negative 16. Which again, I think is way better than the alternative. The alternative would have been to, you know, C1, C2, C3, parameterizations, and then you have to replace your x and y with those parameterizations. I think it would be, we'd still be working on it for sure. All right, take a look at this region D. So we have a hole inside this region, don't we? Want us to consider two paths, two different paths that go along with this region D. C1, which is positively oriented that goes around like this, and C2, which is negatively oriented that goes around like this. All right? Now, imagine we take that region D and we split it into two regions. So D, which was this like donut shaped thing, is now D1, which is the top half of this donut, and D2, which is the bottom half. Okay? So go ahead.
Would it be impossible to consider like C1 and C2 separately and just find the difference? Like C1 being the big one and then C2 being the smaller one, and then just, or do they have to stay within each other and then be divided into?
Well, I think it depends on what it is we're trying to find. So are you saying, like, if we wanted to find the area of D,
Right.
then how would we do it?
We would, for C1 and C2, D within it is just C1 or CS C1 subtracting C2, right? So
Yes, if we wanted the area of D. If we wanted to know the area of D, then we could do line integral along C, right? And then line integral along C2, the other orientation, and then subtract. That should be all right. But that's not what I'm trying to do right now. Just follow with the construction first, okay? That's a good question, but yes, but I'm going somewhere else with this. Okay, so D1 is the top part, D2 is the bottom part, right? Okay. Now consider two new paths. The first path is E1 and the second path is E2. So E1 is this highlighted yellow one. What it does is, let's say it starts here, it goes around, it stops somewhere, right? Not halfway, just somewhere, cuts across, then it goes up over the top half of C2 like that, and then across, and then, you know, that's it. It creates that closed loop, right? There's E1. E2 is also oriented in positive orientation, right? E1 is positive orientation, E2 is also positive orientation. But this time it goes from here, instead of going up, it goes across, down here, across, down, and around. All right? Notice also now, well, maybe I should, yeah, that when I draw E1, right, when I do this, E1 goes like that, over, like that, and across. And then when I draw E2 this way, here, and this way, here, like that, that the E1 and E2 parts on these two pieces cancel one another out, don't they? Because they're basically the same. It would, if I were asked to do a line integral over these two in opposite directions, you would just be changing the sign on them, and so they would be gone, wouldn't they? Okay, let's see if you can make this leap then. Therefore, the double integral, I should probably start with the bottom and conclude with the top. The line integral over C1 plus the line integral over C2 should be equal to the double integral over d1 plus double integral over d2, which is the original double integral over d. So let's see if we can't figure out why that's true. Look at C1 and C2. And I had a better way of showing this before. Let's read it the other way. Maybe it'll be easier to read the other way. So if we want to do the double integral over the whole donut, we want to do the double integral over the whole donut, right, d? Then we split it up into two pieces. d1's on top, d2's on the bottom. But that's saying that all we have to do is add up the line integrals over c1 and c2, right? The reason why we can do that is because we created this path E1 that went like this, round like that, and we combined it together with the one that went this way. And when I put those two together, E1 and E2, when I add those two together, these parts cancel out, right? So if these parts cancel out, I'm back to C1 and C2. It's like, in order to do these two double integrals, I have to do E1 and E2, right? E1 along with E2. But when I do E1 and E2 together, these are gone, which is really back to C1 and C2. Does that make sense? No? No?
Maybe we just have to do a problem.
Well, no, there's not really a problem to do. There is a problem to do, but how about we do this? If we ever have a region that we want to do the line integral of, right, let's call this C, or say we have a region here, D, like that has a hole in it, that if we define an outer curve C1 that goes positive orientation and an inner curve C2 in negative orientation, then the double integral, right, over D of this is equal to the line integrals, these two line integrals, these two together, added together. Right? So if I take the line integral over this, line integral over that, add them together, it's going to be equal to the double integral over that region D.
Even though they're different directions?
That's right, even though they're different directions. We need the different directions so that these parts cancel. Was there a comment?
Isn't that the same thing as what she was saying earlier, kind of, since they're going different directions, it's kind of like taking the two integrals separately and subtracting them to get your,
But instead of subtracting, you're
So if
adding.
they're running the
Well-
same way, you could
Yeah,
make
because
it
you're going-
But with that one, I understand, because you're going the same way throughout the whole thing.
The way I interpreted your question was, what if we were wanting the area? So this would have to be 1.
Or just like how to define D, like. just
The
define-
area of D, right?
Well, whenever we're solving for these, we're solving for the area, yeah? Or
Not all the time, no. I've given you a couple of problems where we solve for the area,
When
but
you're solving for the region D, right? Just in any, when we're solving for our double integral, like to find, I guess whatever we're searching for, couldn't we find with just from the bigger, taking out the smaller kind of thing? Is that what we're establishing, or?
okay. Let me back up. The beginning of this section starts out, says, hey, we have a line integral over a closed curve. If that encloses a region D, then we can convert the line integral to a double integral, right? Second part, we said, hey, if we have a certain type of double integral, specifically one where we're looking for area of a region, then we can convert that double integral into a line integral. That's where we proved the area of a circle was pi r squared, and then that epicycloid, we found the area of that. We were using the double integral of 1 and going backwards, okay? This, we are not finding an area. This is more of, if I have a region Like I said, if I have some donut, right, and I want to know if I break it up into two paths, C1 here going this way and C2 going this way, if I would want to know, this is what I would want to know. If I want to know the line integral over C1 plus the line integral over C2, then that is simply the double integral over D, which is the donut, flat donut, of this partial minus this partial. Okay, all I've done is established a relationship between this and this, given that picture. Okay, so I'm not talking about areas or anything else, just that is the relationship. Draw me a donut, call this C1, call that C2, call D the region between them, and that's our relationship. Now, I haven't used it for anything yet, okay? I just want to see if you believe in the picture. Like, from the picture, do you believe that this is true? I don't know. If it seemed a little skeptical.
I think I see it now. I think I understand it better when you kind of cut it in half like that. But
Yeah.
now I understand it.
I think the way this is the way the book kind of presents it. I think it would be easier if I maybe did this. You know, start out with donut. Well, you know, let's not make our donut weird shaped. Let's just draw a donut, all right? Let's say that we have that, okay? Now, if I call this C1 going around, this, and I call this C2 in the middle, going this way, then please just observe the following. That if I break this up, go this here to here, call that E1, going in that direction, and then I'm out of colors, but now go like this, and call that one E2. Then let's just take a look at that top piece. What does Green's theorem tell us about that? Call this D1. What does Green's theorem tell us about that? The line integral over what?
The C.
Well, no.
The path.
The path, which is E1, right, of P dx plus Q dy, should be equal to the double integral over D1 of partial blah, 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 blah. Yes? That's what that one says. Okay, now let's look at the bottom half. We are positively oriented, right? So that's E2 and that's D2. What does it tell us here?
The line integral.
Line integral over E2, right,
Double integral.
of P dx blah, blah, blah is equal to the double integral over D2 of blah, 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 right? But observe that if I add the paths E1 and E2 together, if I add those two paths together, then what paths do I really have?
Just E1.
If I take E1 and E2 together, add the paths, these middle parts go away, don't they? And so any line integral along here and line integral along here will cancel.
So all you have is E.
So what, instead of this being E1, this is really C1 and C2 when they're put together. And when you put these two together and these become C1 and C2, D1 and D2 becomes D. And that's what this is saying.
So I guess you could say like separately that you have that curtain, like those like lines you drew that'd be the curtains there, but those curtains would cancel out.
Cancel out,
Curtains,
yes.
So you're left with the two circles of curtains.
Yep. I just never have an easy time explaining this. It's always different. I need to change my notes. That's what I need to do. I need to do it different because I think if I just
This way was good.
do it separately and then add them together, I think that works better. Okay, let's just move on. Can you just take that at least right now and just be like, let's proceed? We've got 15 minutes to show the last example. This is a somewhat interesting example. show that the work done along the curve C by the field F dot, by the field F is equal to 2 pi, given that vector field. So we're being told that, look, if we have this vector field, we want to show that the work done by the field moving some object along the path C is equal to 2 pi. And what's our path? Any closed path enclosing the origin. So what makes this problem pretty profound is that you have to show that the work done is equal to a constant. That means it's basically does not depend on the path at all, as long as the path encloses the origin. All right? Not easy to do. This is not easy because, well, where do you start? I mean, what do you do, right? Like, if you try and do this without Green's theorem, you have to find a parametric representation of C, don't you? But C is any path that anyone could come up with, as long as the origin is inside the path. So there's no, like, exact, unique representation of this path. Yet we're supposed to show that for any of the path that anyone comes up with, it's going to be 2 pi. So you can't, like, pick your own path and show it's 2 pi. Because then you have to be able to show that for every path. Showing it 100 times isn't enough. You have to show it's always true. So the way that we're going to go after this problem is not something I think you would naturally come up with. I wouldn't have come up with it. But it shows you the power of something like Green's theorem, and especially what I just showed you a second ago, which we were having trouble with. Okay, so here's the way we're going to do this. We are going to take any path you want. Just imagine you have any path. We're going to call it C. As long as the origin is in here. All right? So the origin has to be inside the path. It cannot be on the path. I think that's implied by the wording. C is any path that encloses the origin. With me? Okay, we're going to assume positive orientation here for C. So C is positively oriented. Now what I'm going to do is I'm going to come up with a new path. And the path that I'm going to choose is a path that goes around the origin, but is inside this curve. And I'm going to choose a circle like this, and I'm going to orient it clockwise, negatively oriented, all right, like this. That's pretty much like what I just had on the board a second ago, isn't it? Now, this, let's call this C2, all right? We never called that C1, did we? Can we leave it as C? Do you understand that that's like C1 from the previous picture? Okay, I'm going to call it C2. Now, do you believe that I can come up with a circle that's going to lie in here? Yes. There is a small enough radius I can pick, right? Agreed? If there's any window between that point and the curve, any gap at all, I can find a small enough circle that this would work. Okay, so I'm choosing that, all right? I'm choosing that, whatever it is. You give me your curve, I will find a circle that will fit inside of it, all right? So that C2, I'm going to define it right now to be R of t equals A cosine t, A sine t, where t is between 0 and 2 pi. That flashing cursor is bothering me. All right, and A has been chosen to be the radius that gets me inside. All right, so that is determined after you give me whatever the curve is, the path. All right. Now what? What did we just conclude? Yeah, we said that the line integral over C, the closed path C, right, of what, f dr Then what? So what did that previous thing say? Bring it up here. Line integral over C1 of, this is work, isn't it? Okay, plus C2, that should be equal to the double integral over D, yes? Okay, so let me, back to this. So I can say that plus what? Plus
The line integral C2.
over C2, which is also closed, right? FDR should be equal to the double integral over D, right? Of the partial of P with partial of Q with respect to X minus the partial of P with respect to Y dA, right? We just showed that in the previous little sketch that we did, and we all buy that? Okay. Let's figure out what this is. Let's figure out what this is. Remember, what we're trying to do is this, right? We're trying to do this. This is what we want to know. But I'm using the result from the previous note that says if we draw it like this, if I come up with this new little curve, then I can say that this plus this equals that. Now, let's do this calculation over here. This is the double integral over D of what is the partial of Q with respect to X. So remember, this is P, this is Q. We might have to do this on the side. What is the partial of Q with respect to X? So you're going to have to take derivative of this. You're going to have to use chain rule, aren't you? Quotient rule? Derivative of the top? 1 times the bottom minus derivative of the bottom with respect to X times the top. So X again, all over, bottom squared. Okay, that's the partial of Q with respect to X, right? Not pretty. What's the partial of P with respect to X? I mean, with respect to Y? Yeah, so we have derivative of the top, which is -1 times the bottom minus derivative of the bottom with respect to Y. 2y times -y, so plus y. How about y squared? Right? Over the same thing. So we're subtracting, so what do we get there? We should be getting, hold on. We should get 0 here. Because we're supposed to do this one minus this one, right? This one minus this one. Let's clean these up a little bit. I don't like looking at that like that. So x squared, let's go x squared plus y squared minus 2x squared. That's same as y squared minus x squared, right? On the top? Yes? Okay, over x squared plus y squared squared. And on the bottom, what do we get?
X squared minus y squared over.
It's the same thing, isn't it? This is minus x squared minus y squared plus 2y squared, which gives you y squared minus x squared again, right? Yes, yes? All over the bottom squared? So what would happen if you took this and you subtracted this? It'd be 0, right? So what does that mean? What's the antiderivative of 0 going to give us? 0. I mean, this is 0. No, we're not saying there's no work. We're saying that these two added up give you no work, right? Y'all see that? Okay. So tell me what that means then. I want to leave this here. This plus this must equal 0, right? which means that the line integral over C, right, is equal to this one over here, negative, right, which is really the line integral over negative C2 f dot dr. And guess what? Negative C2 is this thing moving around like this, right? And this is the way you do that, right? This is the parametrization to move around C2 this way. Right, start at 0, you're going to start there, and then as you let t go, it's going to draw it that way. No one called me out on this earlier, but this does not draw C2 clockwise. This draws it counterclockwise, right? But that's what negative C2 is, isn't it? Y'all understand what I did? Moved this to the other side, which made it negative, but then I just made it a negative path instead. So whatever the line integral is that we're looking for is this one. And what is this? We can do this one. So we have to calculate this, unfortunately. You ready to do it? Okay, great. Let's do it. We have 3 minutes. Okay, so I'm about to do that line integral. Okay, this should be equal to line integral from 0 to 2 pi. Okay, what is this part? It's our field with what plugged in for x and y? Our parametrization, right? So that means we have, what's the first part of this field? Negative y, which for us is negative a sine t, over x squared plus y squared. So what's x squared plus y squared? A squared cosine squared t plus a squared sine squared t. Pull out, so that's just a squared, okay, comma, this one, a cosine t over, same thing. Okay, we're going to dot that with dr, which is the derivative of that, which would be negative a cosine t, and then a sine, whoa, wait, hold on, whoa. A negative a sine t, and then a cosine t, then dt. And now let's dot. So when I do this times this, what do I get? I just get a squared sine squared t over a squared, and the a squareds cancel. So you get sine squared t. And plus the other one? Same story, cosine squared t. So this is really just this. There. Now we got very lucky that that vector field, when we took those partials, canceled, right? It's that particular vector field. That's what they're trying to get us to see here, is that with this particular vector field, the work done on when you move along any path, as long as the origin is in the path, then the work done is 2 pi no matter what. And later on, you might hear about this. This is actually called, what's called like the winding number. The winding number. Winding numbers?
Yeah.
Yeah. If you have a path that goes around like this one time, then you have 2 pi. If you go around twice, you get 4 pi. So it's like a winding number is counting. It's beyond the scope of this class, but it's connected to it. It doesn't matter what path you're taking, though. That's what's crazy. It doesn't matter as long as you're enclosing the origin, you get 2 pi. So it seems like we couldn't have done that, but there was a way. All right, I think that was it for the notes here. Yeah. So we are coming to the end here. How many sections are left? It's 13.9, right? So we have 4 sections left, and we have 5 classes left. And we're going to need all that time, I think. So this is good. We're going to finish the book. I think this is the first time I can say it pretty confident that we will finish the book. All right, do we have a take-home due on Wednesday? There's take-home due on Wednesday. I still haven't graded the ones from last week, sorry. Easter weekend was kind of crazy for my family, so we're done. Have a good day.